So in this little talk, I want to talk about what OghmaNano is. And the answer is really in the second sort of title of this slide, and it's a tool for simulating organic solar cells, perovskite solar cells, OFETs, OLEDs, and any other really disordered or not disordered device that you can think of in both 1D, 2D, sometimes 3D, in time domain, steady state, and frequency domain. So it's a general purpose tool for doing sort of nano and micro simulations of optoelectronic devices. So moving on, I want to talk briefly about the history of OghmaNano, and I think this will help you understand where it's coming from, its history, and how to search for documentation and past papers have used the model. Then I want to talk about an overview of the model. So I'm going to tell you what the model can do, but not necessarily how to do it with the model. You can find that information in later presentations or indeed in the documentation. So here's the history of the model. I started developing it at Imperial College in 2011 and 2012, and it was really written specifically then to simulate organic solar cells. So it was a 1D model specifically for organic solar cells. And I published quite a few papers with it, and I thought, well, it'd be better if other people had access to this as well, not just me, and they get some use out of it. So in 2012, I registered the domain name opvdm.com, which stood for Organic Photovoltaic Device Model, and released it to the web. And it stayed as that for a few years. And then in 2016, I sort of thought, well, there is this perovskite hype going on, and perhaps this isn't such a great name for a simulation tool, bearing in mind it can also simulate perovskite devices. So it was renamed the General Purpose Photovoltaic Device Model, or GPVDM. And then this week, actually, or last week, I decided that GPVDM was actually not a very good name, because since then, or since it was released initially, the model's been now able to simulate lots of other devices apart from just solar cells. So it can simulate transistors, it can simulate OLEDs, it can simulate sensors, it can simulate filters, optical filters, it can do sort of arbitrary ray tracing. So there's a lot of things it can do that aren't necessarily important to solar cells, and it's very useful for other applications. So the other thing was GPVDM was quite hard to say. So I renamed the model this week, and it's called OghmaNano. And it stands for Organic Hybrid Material Nano Simulation Tool. And it's also the name of a Scottish or Irish god, so I thought it was quite a nice name there. So moving on, overview of the model. So this is the overview. So it's got in the model in Ogma, it's got 1D, 2D, and 3D optoelectronic models. So it's got 1, 2, and 3D optical models, and electrical models, and also thermal models. So it's got electrical models, so it's got a drift diffusion models, and it's also got equivalent circuit models. Drift diffusion only goes up to 2D, but the equivalent circuits go from 1 to 3D. It's got optical models, so it's got optical transfer matrix models that are good for simulating things like the solar radiation coming onto a device, or a laser light hitting it, or something like that. It's got 3D ray tracing. It's also got some FDTD, but I'd say that's more beta at the moment, but I hope to improve that soon. It's got excitonic models, so you can sort of model exciton populations in 3D, and we've published some work on that. It's also got singlet and triplet code in it, but I've not released that yet. And it's got, but probably by the time you're watching this video, that will probably be out. It's got PL and EL models. It's got, can work in various steady state, frequency domain, time domain, whatever. It's also got thermal models, so it's got actually a 3D self-heating model, which is 1, 2, and 3D self-heating model. So I'm just going to go through these models and talk about them in a little bit of detail in these next slides. So let's look at drift diffusion. So generally speaking, most people, when they simulate a device, whatever it might be, solar cell or transistor or whatever, they want effectively plots of current against voltage. To do that, you need to do electrical simulations, which is generally speaking drift diffusion equations. So here's some nice current voltage curves that were simulated with model. To do that, just follow the approach as it was used before. So, solve Gauss's law, solve drift diffusion equations, which are there. You don't have to know what all these terms mean, but you probably recognise the form of the equations. And also, the model can do Fermi-Dirac statistics, Maxwell-Boltzmann statistics as well. So it can do the full characteristics or just approximation to them with a Maxwell-Boltzmann approximation, how you like. And in this respect, I guess OghmaNano is quite similar to many other device models, but where it differs quite a lot from a lot of models in literature is its handling of trap states. So if you think about disordered materials, and very often most novel devices are made of disordered materials, because the whole idea is effectively to make, with sort of novel devices, to make them low cost, printable, and as a result of that, the materials aren't that pure, all that ordered, and they're very disordered. So here in the top right, we've got sort of something that might be approximating silicon, so a highly ordered system. It's not got many traps down here in the band gap. But if you look at a material here, like some of these organic materials, they're highly disordered with lots and lots of trap states. In fact, most transport happens through being trapped and then becoming free through sort of thermal activation. And trapping effectively, or transport happens effectively through, generally speaking, through sort of capture escape from traps and sort of getting free, then trapped again, free and trapped again. So they're very, very different materials. So if you want to handle or simulate these disordered materials, you generally speaking need a pretty good model that describes trap states in your device simulator. So you need something a bit more. I'm just going to go back one slide. You need something a bit more than these equations. In fact, quite a lot more. So if this is, imagine our device. So we've got the LUMO, the lowest unoccupied molecular orbital here, and the HOMO, the highest occupied molecular orbital here. And you take a slice through this, so through this band structure of our device, and try and look at these trap states down here. You can sort of write a 0D approximation of this in a cartoon form. So here it is in cartoon form. So here we've got effectively our free carriers that you'd have from the normal drift diffusion model. Here are trap carriers that you'd have from the normal drift diffusion model. And here, between the conduction band and the valence band, you have trap states. So the red ones are electron trap states, and the blue ones are the hole trap states. And the model breaks up in energy space, effectively the energy into different trap states. So here we've got probably about 20 different trap states. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, I don't know, 20 or so trap states. And for each one of these trap states, you solve this trapping escape equation. Basically, you're accounting for electrons getting trapped, electrons getting free, and then into the same trap state, holes getting trapped and holes getting free. And of course, when a hole meets an electron, that's recombination. So by looking at these arrows, you effectively describe both trapping and recombination. And you can do that for each one of these trap states of the electrons and the holes, and you can sort of have a good approximation of what's going on in an organic semiconductor. And this is this is called the Shockley-Reed-Hall recombination model, and it's had quite a lot of success in describing trapping and recombination disordered materials. So if we combine, I'm just going to go back 2 slides. So if we combine this classical drift diffusion model with this sort of trapping and detrapping model, what we can then do is we can draw effectively a picture of our device of effectively carrier density. So the colour is carrier density against energy and against position. So this position in the device, so this is left contact, right contact, and these effects, we're plotting out the density of trapped electrons here. So all these are trapped electrons, and here as well, and these are trapped holes. So we actually visualise the population, the carrier population in our device, say a solar cell or whatever it is, both in position space, which you'd be able to do in a normal model, but in this model, in OghmaNano, you can visualise it also in energy space. And this is really incredibly important for accurately describing the device. I'm not going to go into it here, but there's another video on that. So once you've done this, what you can do is now you can sort of simulate quite accurately steady state curves and transient curves. So these are the left of the steady state curves we looked at earlier, and this is an example from quite an old paper, but these were experiments done. This was transient photocurrent experiments, and so you fire a laser at a solar cell and watch the current transient sort of die off, and these are predictions of the model to the experimental data. So you can see the model sort of quite predictive in many ways. Again, the point of this presentation is to show you the features of the model rather than to go into lots of technical details. So you can also do this in the model. You can do it in 2D, so you can look at OFETs and stuff. So you can look at carrier trapping, detrapping and stuff in 2D. Now, just to polish off this thing, because effectively OghmaNano's party trick is it can do trapping, detrapping really, really well, and sort of carrier dynamics. So all I would say is that if you're thinking of modelling these devices, make sure your device model has such a model in it. There's actually a video here that I'll link to in the description that describes why it is so important to have trap states to accurately describe the physics in these devices. So that's its party trick effectively. The model is absolutely excellent at Schottky Reed Hall dynamic trapping and detrapping and recombination. Right, circuit models. So that's effectively done drift diffusion. Now circuit models. It can do 3D, 1, 2 and 3D circuit models. So you can see here, this is actually a large area solar cell. And this is maybe a few centimetres, and it's got some sort of honeycomb grid printed on top of it. And here is a 3D circuit model of this solar cell, and the yellow bits are sort of individual diodes, and or is it? I think the diode is actually the light blue bit down there. But anyway, so you can do effectively 3D meshes to simulate big devices where drift diffusion becomes too numerically cumbersome. And here's an example. So this was a bit of a printed solar cell taken from a group in Chemnitz, Germany. And this is sort of a 3D model of it, and this is a resistor network of it, and this is then calculating the resistance of various parts of the contact effectively. So it can do that too. And of course, if you can do 3D circuit models, you can also do 1D circuit models. So there's a 1D example of 1D circuit solver in there too. Optical models, so it can do the transfer matrix model. So if you want to know where your photons are in your device, it can just sort of solve the transfer matrix equations, which is quite useful. So you can calculate photon density at different wavelengths, and all these types of good things with different light sources and whatever. You can do ray tracing. So this is sort of quite a nice recent addition to the model. So you can do sort of, for example, scattering of light off films and surfaces, and here's a nice test simulation of a prism. A couple of prisms. You can see the light coming in on the right, and sort of diffraction and things like that going on, and you can see the rainbow of colours coming out of here, which is all simulated. This is sort of this prediction. So it's quite sort of nice to see these accurate results coming out of the model. And here's escape of light from sort of micro lens. So you can do these sort of micro and macro ray tracing simulations. You can also do FDTD. It's FDTD quite a recent addition to the software. So it's more at this stage. FDTD is more toy, whereas the other so the drift diffusion solver I'd say is world class. It's excellent, and so is the trapping model. Ray tracing is fairly good. FDTD is more of a sort of a test, not test, but it's not being used in papers yet, but will be soon. Exciton models. So it's got Exciton models in it, so you can put the Exciton models in 1D in your sort of solar cell, or you can also do sort of 3D Exciton simulations if you're trying to model carriers diffusing away from sort of microscopic domains within the bulk heterojunction of whatever material you're interested in. And you can watch this video on that if you want to, which was published to the front cover of Nature Materials there. So. Simulation modes. So the simulation. So it's got lots of different simulation modes. So these are got from the simulation type menu. So you have sort of steady state JV curves, Sun's VOC, Sun's JSC, CLIV, all types of different transient techniques that you can actually make up your own. So if you want to do TDCF or whatever like that, you can do it. Impedance spectroscopy, all different types of frequency domain stuff, capacitance voltage. All these sort of different EQE, all these things you might possibly want. And here's some examples with a model that was been published already of sort of dark curve, light curve, Sun's VOC, and various frequency domain fits. Thermal models. So it's got again a 3D. It's got a 1, 2, and 3D thermal model in it. It's actually got self-heating in it as well. So you can sort of look at this as an example. I think there's a diode here. As it gets hotter and hotter and hotter, look at the temperature profile across the device. So it's got things like Joule heating and recombination heating in it. So if you want to do thermal heating, you can do that as well. And then example simulations. I think I'm going to end here. So there's lots of example simulations in the model. So if you want to, start off with a simulation that somebody else has already made, you can do. So that thermal simulation that we're looking at is there, at the bottom left. The Exciton simulation I was talking about is there as well. So you can play around to your heart's content. So I hope that's a little introduction to the model. Hope you enjoyed that. Thank you very much for listening.